Welcome to the deep dive. If you're joining us today, you are likely someone who just loves to learn.
Absolutely.
Someone who really wants to cut through all the noise and get straight to the facts, whether you're catching up on the latest in neuroscience or maybe trying to understand your own brain.
Or trying to support a loved one.
Exactly. Yeah. Or if you're just insanely curious about how the human mind works, you're in the exact right place. This deep dive is designed to be your shortcut to being deeply, thoroughly well-informed.
And today's a big one.
It's huge. Our mission today is pretty ambitious. We are going to completely demystify the attention deficit hyperactivity disorder brain.
What we commonly just call ADHD.
Right. And we're moving far, far past the standard behavioral checklist that, you might fill out at a doctor's office. We're looking under the hood. We're going to explore the actual physical wiring of the brain.
Which is where it gets really fascinating.
It really does. We're specifically focusing on the prefrontal cortex, the structural changes, network connectivity, and the regional activation that makes the ADHD brain so unique.
And I just want to say, it's a massive undertaking, but we have an incredibly rich stack of source material to guide us today.
We really do.
We're tracing the scientific journey from foundational papers published back in 2009 all the way up to some absolute cutting-edge machine learning research from 2025.
So we're really spanning the modern era of imaging.
Exactly. We'll be looking at massive meta-analyses, structural MRI data, functional MRI imaging, and even down to the micro-level neurochemical environment of the brain. It's just a fascinating evolution of understanding how this specific brain operates.
It really is. And before we jump into the deep end, I want to briefly establish our objective stance for this conversation.
Good idea.
Because the science of psychiatric conditions, particularly ADHD, it can sometimes intersect with some pretty passionate societal or political debates.
Oh, definitely. Discussions about neurodiversity, medication practices, modern schooling.
Right. Behavioral expectations, all of it. But I want to be clear to you, the listener. This deep dive is strictly a neutral, factual exploration of the peer-reviewed source material we've gathered.
We aren't taking sides.
Not at all. We aren't endorsing specific viewpoints outside of the science. Our goal is just to report the data impartially and convey the ideas contained in the original source material.
Just following the data.
Exactly.
Right.
So, with that established, let's open up the brain. I'd love for you to start us off at the very front. We often hear this area referred to as the conductor of the neurological orchestra.
That's a great analogy.
What exactly are we looking at here, and why is it our starting point for ADHD?
Well, we're looking at the prefrontal cortex, or the PFC. To really understand the neurobiology of ADHD, you have to start by understanding the PFC.
Okay.
It is the most highly evolved part of the human brain. It occupies the very front of your frontal lobes, right behind your forehead.
Like right behind your eyes?
Exactly. You can think of it as the CEO of your brain. It's responsible for human behavior at its absolute highest level, what we call executive functions.
Things like planning.
Planning, organizing, regulating your emotions, holding things in your working memory, and crucially for our discussion today, regulating attention.
So the CEO decides what gets focused on.
Right. And to ground this in the literature, I want to reference a seminal paper by Dr. Amy F.T. Arnsten.
Okay, let's hear it.
This was published in May 2009, appeared in print in 2010 in the Journal of Pediatrics. The title is The Emerging Neurobiology of Attention Deficit Hyperactivity Disorder: The Key Role of the Prefrontal Association Cortex.
That's quite a title. What's the main takeaway there?
Well, in it, she details how the PFC regulates attention and behavior through its widespread connections. I'll quote her directly here. She says the PFC regulates attention and behavior through its widespread connections to sensory and motor cortices and to subcortical structures, such as the basal ganglia and the cerebellum.
I want to pause on that idea of widespread connections because I think it's really easy to imagine the brain as, just a series of isolated compartments.
A lot of people do.
But when Arnsten's paper describes the PFC connecting to sensory and motor cortices and deeper structures like the basal ganglia, it really paints a picture of a central hub.
Exactly. It's the control center.
It's physically reaching out and communicating with the areas that process what you see and hear, the areas that control your physical movement, and those older, deeper areas that manage basic drives.
Yeah, the CEO is talking to all the departments.
So how does the CEO actually manage all those different departments to create what we call attention?
That is the perfect question. And Dr. Arnsten's 2009 paper introduces a really critical distinction that answers it. She outlines two distinct types of attention.
Okay, what are they?
Top-down attention and bottom-up attention.
Top down and bottom up.
Right. She explains that the prefrontal cortex regulates top-down attention. I'll quote the paper again. She writes that it regulates top-down attention, allocating and directing attentional resources based on stimulus relevance.
Based on relevance.
Yes. In contrast, the posterior sensory cortices, so the parts of your brain processing sights and sounds, they mediate bottom-up attention. Meaning they process sensory characteristics based on stimulus salience.
Okay, let me make sure I'm translating this correctly. Top-down attention is effortful and goal-directed, right?
Exactly.
So if you're listening to this right now and you're actively deciding to focus on the neuroscience we're discussing, even if there are other things going on around you, you're using your PFC to exert top-down control. You are prioritizing relevance.
You're forcing your brain to stay on task.
Right. But bottom-up attention, on the other hand, is completely involuntary. It's reflexive. Like if a fire alarm goes off or a glass shatters in the kitchen while you're listening to this, your head snaps toward the noise.
You did decide to do that.
Right. I didn't say, oh, I should focus on the shattering glass. My sensory cortices just reacted to the sudden salience of the sound and completely hijacked my attention.
That is exactly the distinction. And from an evolutionary perspective, both are entirely necessary.
Sure, you need both to survive.
Yeah, you need top-down attention to build a shelter or plan a hunt or finish a spreadsheet for your boss.
Yeah, the boring stuff.
Exactly. But you really need bottom-up attention to avoid getting eaten by a predator that suddenly snaps a twig behind you.
So where does ADHD come into this?
Well, the core neurobiological finding in ADHD, heavily highlighted in this 2009 paper, is that the top-down regulation governed by the prefrontal cortex is inherently weaker.
The CEO is struggling?
The CEO is struggling to maintain its grip on the steering wheel. And when top-down attention is weak, the threshold for bottom-up attention to hijack the system drops significantly.
That makes a lot of sense, but I want to push on that just a little bit.
Sure.
If the top-down control is weak, why does that manifest as the specific symptoms we see in ADHD? Let's take inattention first. Is it that the person literally cannot pay attention? Or is something else happening mechanically?
In neurobiology, we might look at inattention as poor stimulus gating.
Gating, like a literal gate.
Yeah, like a filter.
Yeah.
Because the top-down regulation from the PFC is weak, the brain struggles to gate or filter out irrelevant stimuli.
Ah, okay.
The person appears inattentive to the primary task, say reading a textbook, because their attention is constantly being captured by everything else in the environment.
Everything is salient.
Everything.
Yeah.
The humming of the refrigerator, a car driving by outside, or even their own internal random thoughts. The bottom-up system is constantly overriding the top-down goal.
So it's not a deficit of attention itself.
No, not at all. It is a deficit in the regulation of that attention.
Okay, so the top-down filter isn't strong enough to keep the bottom-up distractions at bay. But what about impulsivity and hyperactivity? Because ADHD isn't just an attention disorder. The H stands for hyperactivity. How does a weakness in the cortex, the thinking part of the brain, cause someone to constantly fidget or blurt out answers? Isn't that a motor control issue?
It is a motor issue, but it originates in the cortex. Remember earlier when we noted that the PFC has widespread connections to the motor cortices and the basal ganglia?
Right, a central hub.
Well, a massive part of top-down regulation is behavioral inhibition.
The brakes.
The brakes. It's the PFC sending a constant active signal to the rest of the brain that says, do not say that thought out loud, or do not jump out of your seat right now, or do not grab that item.
Okay.
Impulsivity is simply the failure of the PFC to successfully inhibit a behavior or an emotional response. Hyperactivity is the failure to inhibit excess motor activity.
Wow.
The body's engine is running, and the PFC's brakes are simply not applying enough pressure to keep the vehicle completely still.
That reframes hyperactivity completely for me. It's literally a failure of neurological braking.
Yeah.
So this brings up a pretty crucial biological question. If the PFC is the CEO and it's responsible for all this vital braking and filtering, why is it struggling to do its job in the ADHD brain?
That's the million-dollar question.
Is the PFC physically damaged? Does it just lack the power it needs to send those signals?
To answer that, we have to zoom way, way in, down to the microscopic level of the neurochemical environment.
Let's do it.
The prefrontal cortex is an incredibly sensitive, highly evolved network of neurons. It's not robust like some of the older, deeper, more primitive parts of the brain that control things like breathing or your heart rate.
Those keep running no matter what.
Exactly. But the PSC requires a highly specific, perfectly balanced chemical environment to function. It is heavily reliant on a delicate balance of neurotransmitters.
So what exactly are the chemicals that the PFC needs to function properly? Are we talking about serotonin or endorphins or something else?
We need to consult another foundational paper for this.
Okay, what's the source?
This one is from August 2011, published in the journal Pharmacology, Biochemistry, and Behavior, written by Amy F.T. Arnston and Stephen R. Pliska.
Same author as before.
Yes, Arnston is a pioneer here. The title is Catecholamine Influences on Prefrontal Cortical Function, Relevance to Treatment of Attention Deficit Hyperactivity Disorder and Related Disorders.
Catecholamines.
Yes. In this paper, they explicitly detail how the PFC is uniquely sensitive to its neurochemical environment. They point out that relatively small changes in the levels of two specific chemicals, norepinephrine and dopamine, can produce massive, significant changes in how the PFC functions.
Norepinephrine and dopamine. Okay, these belong to that class of neurotransmitters called catecholamines.
You got it.
Now, I hear about dopamine all the time in the context of reward and pleasure, like getting a notification on your phone or eating a piece of chocolate.
The classic dopamine hit.
Right. But why are dopamine and norepinephrine so critical for the...
It comes down to how these two chemicals cooperate to manage information processing at the cellular level. Think of the prefrontal cortex as a complex radio receiver trying to tune in to a very specific station.
Okay, I like this analogy.
To hear the broadcast clearly, you need a strong signal from the station you want, and you need minimal static or background noise from all the other stations.
Makes sense.
Norepinephrine, which we can call NE, is responsible for increasing the signal.
How does it do that?
It does this by stimulating specific receptors on the neurons called postsynaptic alpha-2A adrenoceptors.
Alpha-2A adrenoceptors.
Yes. When NE binds to these alpha-2A receptors, it literally strengthens the connectivity of the neural networks that are actively processing the relevant information. It amplifies the network you want to use.
Okay, so norepinephrine is turning up the volume on the, say, classical music station I'm trying to focus on. It's reinforcing the specific neural pathway related to my current goal.
Yeah.
But obviously, just turning up the volume isn't enough if there's a ton of static competing with the music. You're just making the static louder, too.
Precisely. And that is where dopamine, or DA, comes into play in the prefrontal cortex. Dopamine acts to decrease the noise.
Okay, so it handles the static.
Yes.
Yeah.
It does this by stimulating D1 receptors. When dopamine binds to D1 receptors in the PFC, it actively suppresses the firing of neurons that are responding to irrelevant, distracting stimuli.
It dampens the background chatter.
Exactly. So you have norepinephrine increasing the signal through alpha-2A receptors and dopamine decreasing the noise through D1 receptors.
Whoa.
Together, when they're at optimal levels, they create a sharp, clear, high-contrast focus. This is the physiological state that allows the PFC to exert strong top-down control.
The signal-to-noise ratio, that is an incredibly elegant biological system.
It really is.
So, in the context of ADHD, the implication of the Arnston and Pliska paper is that this delicate neurochemical environment is off balance. The levels of available dopamine and norepinephrine in the PFC are just out of that optimal zone.
Yes. The signal is too weak and the noise is too loud.
Which means?
When that happens, the networks in the prefrontal cortex essentially disconnect. The CEO loses communication with the rest of the brain, the brakes fail, the filter fails, and bottom-up attention just takes over.
This actually brings up a question about how we treat ADHD medically. Because if the issue is this specific imbalance of norepinephrine and dopamine in the prefrontal cortex, how do the standard treatments actually interface with these receptors?
There's a very direct interface.
Because for decades, there's been this public paradox, right? Why do doctors give stimulant medications, which sound like they would make you more hyper, to people who are already hyperactive? It sounds totally counterintuitive.
It does. But once you understand the PFC's desperate need for these specific catecholamines to apply the neurological brakes, the paradox completely disappears.
Okay, walk me through it.
Therapeutic, clinical doses of stimulant medications, things like methylphenidate or amphetamines, they have a preferential effect on the prefrontal cortex. At the synaptic level, these medications block the reuptake transporters.
Reuptake transporters.
Right. Normally, after dopamine and norepinephrine are released into the synapse to send a signal, transporters act like little vacuum cleaners.
Sucking up the extra.
Exactly, sucking the chemicals back up to be recycled. Stimulants block those vacuums. This effectively leaves more dopamine and norepinephrine floating in the synapse, increasing their availability to bind to those D1 and alpha-2A receptors.
So by leaving more of these chemicals available in the gap, the medication is artificially bringing the brain back into that optimal signal-to-noise zone.
You got it.
It gives the PFC the chemical fuel it needs to finally apply the brakes to the motor cortex, which reduces the hyperactivity, and to filter out the background noise, which reduces the inattention.
That's the exact mechanism.
That makes perfect biological sense. But wait, what about non-stimulant medications? I know there are drugs like guanfacine used for ADHD.
Yes, widely used.
If those aren't stimulants, and they don't touch dopamine, how can they possibly be effective if we just establish that the ADHD brain needs both chemicals to fix the signal-to-noise ratio?
That is a fantastic nuance to explore. You are absolutely right. Guanfacine does not block the reuptake of dopamine. Instead, guanfacine is an alpha-2A adrenoceptor agonist.
Agonist meaning it mimics something.
Exactly. Its molecular structure is similar enough to norepinephrine that it can directly bind to and stimulate those specific alpha-2A receptors in the prefrontal cortex.
Oh, wow.
By doing so, it specifically mimics the action of norepinephrine. It artificially boosts the signal and strengthens the network connectivity in the PFC.
So it's only fixing half the equation, but it's enough.
Yes. Even without fixing the dopamine noise issue directly, strengthening the primary signal pathway significantly improves top-down regulation and behavioral inhibition. This offers an alternative biological mechanism for treatment, particularly for patients who maybe don't tolerate stimulants very well.
It's fascinating how targeted that is. We've gone from the macro behavior of, a child fidgeting in a classroom, all the way down to the microscopic binding of a specific molecule to an alpha-2A receptor.
That long chain of cause and effect.
But I have to ask, are the differences in the ADHD brain purely chemical? Is it just a matter of the fluid levels being off in an otherwise identical brain? Or is the actual physical hardware, the structure of the brain itself, different?
That is a critical realization in modern neuroscience. And it really represents a massive shift in how we understand the disorder. The ADHD brain is physically, structurally different from a neurotypical brain.
Physically different.
Yes. And we aren't just guessing based on a few small studies here. We have highly robust, massive sets of data to support this now.
Let's hear the sources.
To cover the structural aspect, we're drawing from several major review papers. First, Stephen V. Farrell's comprehensive 2024 paper, Attention Deficit Hyperactivity Disorder, published in Nature Review's Disease Primers.
Okay, very recent.
Second, Edmund J. Sanugabark's 2022 Annual Research Review, published in the Journal of Child Psychology and Psychiatry. And third, a highly detailed paper by Katia Rubia from 2014, Imaging the ADHD Brain, Disorder Specificity, Medication Effects, and Clinical Translation, published in the Expert Review of Neurotherapeutics.
Man, that is a heavyweight lineup of sources, really spanning a decade of advanced imaging research. So let's dig into the physical structure of the brain. What are these massive reviews actually telling us about the anatomy?
Let's look at the Sanugabark 2022 paper first.
Sure.
Sanugabark's 2022 review synthesizes decades of MRI research. He notes that comprehensive meta-analyses consistently confirm two major structural differences.
Which are?
First, a slightly reduced total brain volume. Second, and much more importantly, smaller, localized gray matter volumes in very specific regions.
Which regions?
Particularly the putamen, the globus pallidus, the caudate, and the anterior cingulate cortex, or the ACC.
Okay, I want to break down what those specific regions do, because throwing out terms like globus pallidus can sound like a foreign language to a lot of people.
Fair enough.
But first, just to be completely clear, a slightly reduced total brain volume has absolutely nothing to do with a lack of intelligence, correct?
Correct, nothing at all.
It just means the physical volumetric footprint of the brain is marginally smaller overall.
Exactly. Brain volume does not correlate directly with intelligence in this context. It is a biological marker of a developmental variance, not a measure of cognitive capacity. So we can put that misconception to bed right away.
Okay, good to clarify. Now, what about those specific regions? The putamen, the globus pallidus, and the caudate. What are these structures doing in a neurotypical brain on a Tuesday afternoon?
Those three structures, the putamen, globus pallidus, and caudate, together, they make up a large part of what we call the basal ganglia.
The basal ganglia, we mentioned that earlier with the Arnston paper.
We did. These are deep subcortical structures. They sit underneath the wrinkly cortex. The basal ganglia are heavily involved in motor control, but they're also deeply involved in habit formation, reward processing, and procedural learning.
Oh, wow. Reward processing.
Yes. Remember earlier when Arnston's paper mentioned the prefrontal cortex has widespread connections to the basal ganglia?
Right.
Well, the PFC relies on these structures to help execute its plans. If the volume of gray matter in these relay stations is smaller, the neural circuitry simply isn't as robust. The CEO is calling down to a department that is literally understaffed.
That paints a very clear picture. And what about the anterior cingulate cortex, the ACC? What does that do?
The ACC acts as a major hub for emotional regulation, error detection, and reward anticipation. It works closely with the prefrontal cortex to monitor performance and signal when you need to adjust your behavior.
Error detection, like noticing you've made a mistake.
Exactly. So when MRI meta-analyses show reduced gray matter volume in these specific subcortical and cingulate regions, it provides a physical map of the behavioral symptoms.
The hardware itself.
Yes. The hardware responsible for motor control, reward processing, and error detection is physically smaller.
How confident are we in these structural findings, really? Because you mentioned meta-analyses, but I know that early in the history of brain imaging, MRI studies were notoriously inconsistent.
They definitely were.
Like one study with 15 college students would find something, and then another study with 20 adults would find the exact opposite. How did the field actually overcome that?
You're highlighting a very real historical issue in neuroscience, the problem of reproducibility due to small sample sizes. To solve this, the scientific community formed the ENIGMA Consortium.
ENIGMA.
Yes, you'll see this referenced heavily in our 2020 source by Pereira Sanchez and the 2017 paper by Hugman. ENIGMA stands for Enhancing Neuroimaging Genetics Through Meta-Analysis.
Okay, so a massive collaboration.
Massive. Instead of running a new study with 20 people, researchers around the entire globe agreed to pool their existing brain scan data. They compiled structural MRIs from thousands and thousands of individuals, both with and without ADHD.
So instead of looking at a tiny pond, they analyzed the entire ocean.
Exactly. These are called mega-analyses. And when you run the statistical analysis on thousands of brain scans simultaneously, the noise drops out and the true biological signals emerge.
And what did they find?
The ENIGMA mega-analyses definitively confirmed that these subcortical brain volume differences, the smaller basal ganglia regions, are not flukes. They are real, consistent physical hallmarks of the ADHD brain across populations.
The sheer scale of that data completely removes any doubt. It's structural. But I understand from the literature that it's not just that the brain is built differently in its final adult form. It's also about when and how it builds itself during childhood and adolescence.
Yes, the timeline matters immensely.
And this brings us to a really profound concept in the research: maturational delay. Let's look at Katia Rubia's 2014 paper in the Expert Review of Neurotherapeutics. She states something really fascinating.
I'm going to quote well.
She writes, ADHD is characterized by a delay in brain structure maturation, which possibly extends to brain function and structural and functional connectivity. So what exactly does a delay in brain structure maturation look like physically?
To understand this, we have to look at how a healthy brain develops over time. When a neurotypical brain develops through childhood and into adolescence, the cortex, the outer wrinkly layer of the brain, goes through a highly orchestrated sculptural process.
Like molding clay.
Sort of. Initially, it thickens as neurons grow and make connections, but then, as the brain matures and becomes more efficient, it goes through a process of pruning, or cortical thinning.
Pruning, like trimming a bush.
Very much like that. The brain eliminates unused connections to streamline its processing power, while the overall surface area expands and folds. This trajectory of thickening, followed by targeted thinning and surface area expansion, is the physical manifestation of brain maturation.
It's like a sculptor adding a bunch of clay to rough out the general shape, and then meticulously carving it away to reveal the final, precise statue.
That's a beautiful way to picture it.
So what happens in the ADHD brain during this developmental window?
Longitudinal MRI studies, where they scan the exact same children year after year as they grow up, have shown that the ADHD brain follows this exact same trajectory of cortical thickening and pruning.
Okay, so it does happen.
It happens. However, the timeline is significantly shifted. It is delayed. For example, the peak of cortical thickness in the prefrontal regions, which is the necessary precursor to that efficient pruning process, might occur several years later in a child with ADHD compared to their neurotypical peers.
Years later.
Yes.
Yes.
The sculptor's doing the exact same work, but they started on the project 3 to 5 years late.
Wait, if a cortex is supposed to thin out and prune itself to become efficient as an adult, why is a delay in thinning a problem for a child.
Because the child is being asked to navigate an environment like a rigid classroom setting
Yeah.
that expects their brain to be at a specific maturational milestone.
Oh, I see.
If a 10-year-old with ADHD has the prefrontal cortical maturation of a 7-year-old, they simply do not have the physical neural infrastructure to sit still, inhibit their impulses, and exert top-down attention for 6 hours a day. It is physically impossible for them. The hardware just hasn't finished compiling yet.
I really want to emphasize why this matters so much to you, the listener. Because if you are an adult who grew up with ADHD, or if you're currently raising a child with ADHD, you have undoubtedly encountered the stigma.
It's everywhere.
The societal narrative that ADHD is just a behavioral choice, that it's a lack of discipline or laziness or a result of bad parenting.
Which is incredibly damaging.
Right. But these structural findings, the reduced volumes in the basal ganglia confirmed by thousands of Enigma scans, the documented physical delay in how the cortex matures and prunes itself, this is the ultimate validation.
It really is.
ADHD is a profound neurobiological reality. You cannot discipline a child into maturing their cortical surface area faster. You cannot try harder to increase the gray matter volume in your anterior cingulate cortex. It fundamentally shifts the entire paradigm. It moves ADHD from a moral failing or a character flaw to a clearly defined biological variance.
That is perhaps the most crucial takeaway from the structural imaging data. It forces a reframing of the entire conversation around accommodation, scaffolding, and medical support rather than punishment and shame.
Absolutely. So we've looked at the chemicals, the neurotransmitters floating in the synapses, and we've looked at the static structural architecture, the gray matter volumes and cortical thickness.
Oh, yeah, hardware.
Right. But a static MRI is essentially just a high-resolution photograph. It tells us what the hardware looks like when it's turned off. What happens when we ask this unique brain to actually do something? How do we watch the software run?
For that, we have to transition from structural imaging to functional imaging, specifically functional magnetic resonance imaging, or fMRI.
I want to make sure we understand the methodology here before we dive into the results. An fMRI machine looks exactly like a regular MRI tube, right?
It's the same machine, yes.
So how does it capture a video of the brain working rather than just a photograph of its shape?
An fMRI doesn't measure brain matter directly. It measures blood flow. It relies on something called the BOLD signal, blood oxygen level dependent signal.
Bold D signal.
Yes. When a specific region of your brain becomes active because you're performing a task, those neurons require more energy. Therefore, the body routes more oxygen-rich blood to that specific region.
Supply and demand.
Exactly. The fMRI scanner is incredibly sensitive to the magnetic differences between oxygen-rich and oxygen-poor blood. So by tracking the blood flow in real time, we can map exactly which areas of the brain are demanding energy and therefore lighting up during specific cognitive tasks.
It's essentially tracking the metabolic footprint of a thought.
That is exactly what it's doing.
So, you put a person with ADHD into an fMRI scanner, you give them a task to do on a little screen inside the tube, and you track the blood flow. What does the data tell us?
To synthesize this massive area of research, we're looking at Katya Rubia's March 2018 paper, Cognitive Neuroscience of Attention Deficit Hyperactivity Disorder, ADHD, and its clinical translation, published in Frontiers in Human Neuroscience.
Okay.
In this comprehensive review, she summarizes the functional imaging data with a very dense but highly precise statement. She writes, ADHD patients have cognitive domain-dissociated complex multisystem impairments in several right and left hemispheric dorsal, ventral, and medial, frontocingulostriatothalamic, and frontoparietocerebellar networks.
Wow. Okay, that is a massive wall of pure neuroscience jargon.
With a mouthful.
Let's translate that into plain English so we can actually understand what is failing in the scanner. Cognitive domain-dissociated complex multisystem impairments. If I'm understanding this, cognitive domain-dissociated means the impairment isn't just a single constant failure. It changes depending on what cognitive domain or what task you ask the brain to perform.
Correct.
And multisystem impairments means it's not just one broken neuron, it's entire systems. And all those long hyphenated words, frontocingulostriatothalamic, those are just the anatomical highways connecting the front of the brain to the deep structures and the back of the brain.
Exactly. The brain operates on neural highways. And the fMRI data shows that in ADHD, depending on what vehicle is trying to drive, whether it's an inhibition task, a working memory task, or a timing task, Different highway networks experience massive traffic jams or power failures.
Okay, that makes sense. Let's look at the specific fMRI tasks that prove this, starting with the cognitive domain of inhibition.
Right, behavioral inhibition. We talked about how the PFC is supposed to act as the brakes.
How do scientists actually isolate breaking in an fMRI scanner?
They use specific, highly controlled psychological tests, the most common being the stop signal task.
Stop signal. How does it work?
In the scanner, the participant watches a screen. They are instructed to press a button as quickly as possible every time they see an arrow pointing left or right. This builds up a pre-potent motor response. They get used to quickly hitting the button.
Left, right, left, right. You get it into a rhythm.
Yes. But occasionally and unpredictably, a stop signal appears right after the arrow, like a red light or a loud beep. The participant has to suddenly inhibit their impulse and not press the button.
Oh, that sounds hard.
It forces the brain to suddenly slam on the brakes.
I can imagine that being incredibly frustrating, especially inside a loud MRI tube. So when a neurotypical brain slams on the brakes during that task, what lights up? And how is it different in the ADHD brain?
In neurotypical brains, successfully stopping that motor action heavily recruits and demands blood flow in the right inferior frontal cortex, or IFC, and the supplementary motor area, or SMA. These regions just light up brilliantly on the scan.
The brake lights come on.
Yes. But in patients with ADHD, meta-analyses of functional imaging consistently show significant underactivation in these specific right hemisphere regions. The blood flow doesn't surge, the metabolic energy just doesn't arrive.
So the hardware is there, but it's not powering up.
Exactly. The brakes are physically not getting enough power to stop the action.
That maps perfectly back to everything we discussed about impulsivity and the lack of top-down control. The structure of the cortex is delayed in maturation, the dopamine signal within it is weak, and when you actually watch it in real time trying to do its job on a screen, the braking center of the brain simply doesn't activate the way it should.
The biological chain of evidence is incredibly strong here.
It really is. But inhibition is only one cognitive domain. What happens when we test a different highway? What about how the ADHD brain processes time?
This is one of the most fascinating and clinically relevant areas of fMRI research. For this, we reference an August 2012 paper by Hildred Hart, Joaquim Marodua, David Matei-Coles, and Katia Rubia.
Rubia again, she's prolific.
Very. It's titled Meta-Analysis of fMRI Studies of Timing in Attention Deficit Hyperactivity Disorder, ADHD, published in Neuroscience and Biobehavioral Reviews. Timing functions like estimating how long a task will take, reproducing a rhythm, or waiting for a delayed reward. These are historically profound difficulties for individuals with ADHD.
I'm really hung up on this concept, to be honest. How does the brain actually tell time? We don't have a literal ticking clock in our skull. How do we test timing in a scanner?
Scientists use time discrimination tasks or time reproduction tasks. For example, a participant might see a shape appear on the screen for exactly 1.2 seconds. Then they're asked to hold a button down for that exact same duration.
Just guessing based on feel.
Right. To do this accurately, the brain has to generate internal temporal markers, as to count the beats without a metronome. The Hart 2012 meta-analysis found that during these timing tasks, ADHD patients show significant, quote, reduced activation in typical areas of timing, such as left inferior prefrontal cortex, IFC insula, cerebellum, and left inferior parietal lobe.
The cerebellum, I always learned that the cerebellum, that little structure at the base of the brain, was just for physical balance and motor coordination. What is it doing with time?
It was historically viewed purely as a motor structure, yes, but modern neuroscience has revealed the cerebellum is deeply involved in timing, sequencing, and rhythm across cognitive domains, not just movement.
Oh, that is wild.
The left IFC, the insula, and the cerebellum form a network that acts as the brain's internal metronome. They literally encode the passage of time. And in the ADHD brain, this metronome network is underactivating. The Bold-D signal is blunted.
I really want to highlight how significant this is for the lived experience of ADHD. We almost exclusively refer to it as an attention disorder, but this fMRI data shows it is fundamentally a timing disorder as well.
Yes, absolutely.
If your internal metronome is underactivating, if it's running too slow or skipping beats entirely, your perception of reality is structurally distorted.
Yes. This biological deficit in the left hemisphere and cerebellum is the direct mechanical cause of what we clinically refer to as time blindness.
Time blindness.
Time blindness is the profound inability to sense the passage of time accurately. It's why someone with ADHD might sit down to check a single email, follow a rabbit hole, and suddenly realize 3 hours have vanished.
They didn't feel the hours pass.
Right. The brain is simply not generating the internal temporal friction that alerts a neurotypical person, hey, it's been a long time, we should transition to a new task.
Hmm.
The biological clock is disconnected from their conscious awareness.
That completely explains why setting a physical timer is so often recommended for ADHD. You literally have to outsource the executive function of timekeeping to an external device because your insula and cerebellum aren't handling the job internally.
You're providing an external metronome.
And it also perfectly explains the concept of delay aversion. If your internal clock is broken, waiting for a delayed reward doesn't just feel mildly annoying. It feels subjectively intolerable.
Because the future isn't mapped out properly.
Right. Let's say I offer you a choice. I'll give you $10 today or $20 tomorrow. A neurotypical brain recruits its timing networks, projects itself into the future, accurately maps the duration of one day, and calculates that's a good return on investment, I will wait.
The math makes sense.
But if your brain struggles to biologically construct the temporal feeling of tomorrow, the wait feels infinite. So you grab the $10 today. It's not a moral failing or a lack of willpower. It's a mechanical failure of the biological hardware responsible for temporal processing.
That is a phenomenal synthesis. And if we connect this to the bigger picture, we really start to see a theme. We have these isolated regional deficits. The underactive right IFC failing to apply the brakes, the underactive left IFC and cerebellum failing to keep time.
Lots of broken parts.
But these regions do not exist in a vacuum. They have to communicate. The brain operates as a series of interconnected, large-scale networks. And this brings us to the next crucial level of our deep dive, network connectivity, and specifically, the role of the default mode network.
Right, moving from the isolated regions and the specific traffic jams to the entire grid. We have an excellent source summarizing this paradigm shift. It's the April 2020 monograph titled simply The Neurobiology of ADHD.
Yeah.
It lays out how we've moved beyond looking at single brain areas. The authors note, quote, dysfunctional brain areas frequently implicated in the pathophysiology of ADHD are the prefrontal cortex, anterior cingulate cortex, ACC, parietal cortex, striatum, and cerebellum.
We've discussed all these regions individually. The prefrontal cortex for top-down control, the striatum and the basal ganglia for reward, the cerebellum for timing.
Right.
But modern network neuroscience looks at how these regions sync their firing patterns together over time. In the brain, we have distinct, large-scale networks that alternate their dominance based on what we are doing.
Okay.
One of the most important is the cognitive executive network, or CEN. This is a task-positive network. It powers up and syncs together when you're actively focusing on an external goal.
Like solving a complex math problem.
Or writing a report, or listening closely to instructions.
So it's the getting things done in the external world network.
Exactly. Conversely, we have a network called the default mode network, or the DMN. This is considered a task-negative network. It turns on when your mind is at rest, when you are not focused on the outside world.
What's it doing when it's on?
The DMN is responsible for daydreaming, reflecting on past memories, anticipating the future, and internal self-referential thought.
Just your inner monologue and imagination.
Right. And in a healthy, neurotypical brain, these two networks, the CEN and the DMN, are highly anti-correlated. They operate on a strict neurological seesaw.
A seesaw.
Yes. When you need to focus on a task, the cognitive executive network activates, and it actively suppresses or deactivates the default mode network. You stop daydreaming so you can focus on the math problem.
So the brain forces you to close the internal tab so you can focus on the external window.
Perfect analogy.
What happens to the seesaw in the ADHD brain? Why does it fail?
Let's bring back Katya Rubia's 2018 paper on cognitive neuroscience. She provides the exact mechanism. She writes, poor deactivation of the default mode network, DMN, suggests an abnormal interrelationship between hypo-engaged task-positive and poorly switched-off hyper-engaged task-negative networks.
Poor deactivation of the default mode network. This is a profound insight. In ADHD, the seesaw is fundamentally broken.
It's jammed.
When the person tries to focus their attention on a task, their task-positive networks, the cognitive executive network, are hypo-engaged, meaning they don't power up strongly enough.
We already discussed the chemical reasons for this.
Right, the weak dopamine and norepinephrine signals in the prefrontal cortex. But the second half of that quote is equally important. The task-negative network, the daydreaming default mode network, is poorly switched off. It remains hyper-engaged.
Yes.
The brain physically fails to suppress the internal daydreaming network while simultaneously trying to perform the external task.
Exactly. Both networks remain active at the same time. competing for limited cognitive resources. The internal noise is just as loud as the external signal.
I think this leads to my absolute favorite analogy for understanding the subjective experience of ADHD.
Let's hear it.
Imagine you're trying to listen to an incredibly important, highly complex phone call. Maybe it's your boss giving you specific instructions for a huge project. To do this, you absolutely need your task-positive cognitive executive network to be fully engaged.
You need to be locked in.
Locked in. Now imagine that sitting right next to you on the desk is a radio. And because your brain's seesaw is broken and cannot suppress the default mode network, that radio keeps randomly turning itself up.
On its own.
Right. It starts blasting a catchy snippet of a pop song from the 90s, or suddenly plays an anxious thought about a conversation you had yesterday, or interrupts with a sudden curiosity about how a toaster works.
While you're on the phone with your boss.
Exactly. You are trying desperately to hear the phone call, to maintain your top-down attention, but the internal radio keeps hijacking your focus.
That analogy is biologically accurate. That neural intrusion from the default mode network is the actual neurobiological mechanism of internal distractibility.
It's an intrusion.
When a person with ADHD loses focus, it isn't always because a siren went off outside or a notification popped up on their phone. Very often, the distraction is generated entirely from within.
The radio turns on.
Right. Their own default mode network intrudes on the workspace of their task-positive network, breaking their train of thought. This failure to suppress the DMN is one of the most reliable and hallmark network signatures we see in the ADHD brain.
It validates the experience so perfectly. The internal distraction is just as potent and just as involuntary as external distraction. It is all competing for the exact same limited bandwidth.
It really is exhausting.
So let's take stock of where we are in this deep dive. We've gone from the microscopic molecules of dopamine floating in the synapses to the gross structural volumes of the basal ganglia measured by thousands of MRI scans.
We've covered a lot of ground.
We've watched the brain fail to apply the brakes in real-time fMRI blood flow analysis, and we've explored how entire brain-wide networks fail to coordinate their seesaw dynamics. This brings us to our final section. The cutting edge.
This is where it gets really exciting.
Where is the science going right now? How are researchers using modern technology like big data and artificial intelligence to refine our understanding of ADHD?
The field is moving incredibly fast, and the trajectory is pointed entirely toward precision and individualization.
Moving away from the checklist.
Exactly. Historically, because we didn't have these imaging tools, ADHD had to be treated as a somewhat uniform behavioral diagnosis. It was divided into subtypes like predominantly inattentive or combined type, purely based on which boxes a patient checked on a questionnaire.
Right, symptom tracking.
But modern imaging is proving that these behavioral categories are actually distinct neurobiological realities. For instance, a 2020 paper by Saad et al., published in Frontiers in Integrative Neuroscience, highlights this perfectly.
Okay, SOD 2020.
It's titled, A Systematic Review of Imaging Studies in the Combined and Inattentive Subtypes. They point out that different clinical subtypes, those with combined hyperactivity and inattention versus those with purely inattentive symptoms, actually show distinct structural and functional network organizations in the brain.
That is a massive paradigm shift. It means someone who is purely inattentive doesn't just have a milder version of ADHD. Their brain networks are fundamentally organized differently than someone who presents with hyperactive and impulsive symptoms.
It's a different biological flavor of the disorder.
But how are we mapping these differences in a way that is actually useful for a doctor or a patient? Just knowing it's different doesn't help me in the clinic.
That is where the big data and AI come in. I want to highlight a highly influential 2020 paper by Cura, Sanchez, and Castellanos in the journal Current Opinion in Psychiatry.
What are they proposing?
They discuss the intensive push in neurobiology toward creating a predictum of mental illness.
A predictum.
Yes. This involves taking these vast sets of neuroimaging data, the ENERGY structural scans, the fMRI functional scans, and feeding them into complex machine learning algorithms. The algorithms are tasked with finding hidden biomarkers and mathematical patterns in the brain's structure and connectivity that are simply too complex for the human eye or standard statistical models to identify.
A predictome. It sounds like something straight out of science fiction. using AI to mathematically predict and categorize the physical state of a psychiatric condition.
It's becoming reality.
And this leads us to the absolute latest research we have in our stack. We have a paper here from 2025 by Chen et al. The title alone tells you exactly where the future of this field is heading.
It really does.
It's titled Distinct Neuroimaging Subtypes of ADHD Among Adolescents Based on Semi-Supervised Learning. What exactly are Chen and his team doing here that is so revolutionary compared to the 2014 or 2018 studies we looked at?
The Chen 2025 paper represents a masterful convergence of everything we've discussed today. Previously, studies usually looked at structure, or they looked at function, or they looked at chemistry.
In isolation.
Right. Chen's team integrated them. They used a type of artificial intelligence called semi-supervised machine learning to map the density of specific neurotransmitters directly onto the physical structural maps of the brain's cortex.
Okay, merging maps.
Specifically, they used normative data from PET scans, which can visualize receptor density, to map where dopamine D1 receptors, D2 receptors, and dopamine transporters, or DA, are most heavily concentrated.
So they mapped the chemical hotspots?
Yes. They then overlaid that chemical map onto the structural MRI scans of adolescents with ADHD.
I want to make sure I grasp the methodology here because it's brilliant. A standard structural MRI, as we established, just shows water and fat. It shows the gray and white matter volume. It can't see dopamine. Not at all. But they took separate data that does show where dopamine receptors cluster, and they used AI to merge these two data sets together. They basically asked the computer, show me how the chemical architecture relates to the physical architecture.
That's exactly what they did.
And what did the AI find when it looked at that complex overlap?
By analyzing these incredibly complex multimodal overlaps, the machine learning model successfully and reliably identified 3 distinct neuroimaging subtypes of ADHD.
3 distinct types.
Yes. The AI categorized them based on how the neurotransmitter density aligned with structural cortical variations. They named them the underdeveloped subtype, the overdeveloped subtype, and the mixed subtype.
Wow.
The algorithms found mathematical patterns in the biology that can reliably categorize the brains, entirely separate from taking a behavioral questionnaire or observing a child in a classroom.
So the AI essentially said, forget the behavioral symptoms for a moment. Based purely on the physical shape of the cortex and the density of dopamine receptors, these brains fall into 3 distinct biological clusters.
Completely objective biological clusters.
What does this mean for the future? If I'm a listener sitting in a psychiatrist's office tomorrow, how does this AI research eventually change my life? Because right now, finding the right ADHD medication is often an exhausting months-long process of trial and error.
It's very frustrating for patients.
You try a stimulant. If it causes severe anxiety, you switch. If it doesn't last long enough, you adjust the dose. If that fails, you try a non-stimulant, like guanosine. It's a guessing game based on behavioral feedback. Will these AI-driven fMRI classifications eliminate that guessing game?
Eliminating the guessing game is the ultimate goal of this research. The extrapolation here points clearly toward an era of personalized precision neurotherapy.
Precision medicine.
Yes. As Katia Rubio pointed out in her earlier reviews, pattern recognition using fMRI diagnostic classifications has already shown over 80% accuracy in controlled studies just for diagnosing ADHD versus a neurotypical brain.
Over 80%, that's huge.
As the technology in the Chen 2025 paper matures and becomes clinically viable, we are looking at a future where a patient comes in, receives a rapid multimodal brain scan, and the machine learning algorithm identifies their specific neurobiological subtype.
So the doctor could look at the scan and say, the AI identified that you have the underdeveloped D1 receptor subtype.
Exactly. And because we will know exactly how that specific biological profile responds to different chemicals, the doctor can prescribe a highly specific neuromodulation therapy or a targeted pharmacological treatment tailored exactly to that individual's brain.
Just bypassing the trial and error completely.
It removes the behavioral trial and error. It moves psychiatry away from a subjective behavioral science and grounds it firmly as a precision biological science. It means faster relief, highly targeted dosages, and significantly fewer side effects because you are giving the brain exactly what its specific architecture requires.
That is an incredibly hopeful, inspiring vision for the future of treatment. It provides a profound validation of the individual's unique biology, replacing frustration with real, data-driven precision.
It's going to change lives.
Let's synthesize this incredible journey we've been on today. We started at the absolute microscopic level We looked at the neurochemical environment of the prefrontal cortex, understanding how dopamine and norepinephrine must perfectly balance the signal-to-noise ratio in those delicate D1 and alpha-2A receptors to allow for top-down executive control.
The signal and the noise.
We then zoomed out to look at the physical volumetric structure of the brain. We saw how massive global enigma studies prove that the ADHD brain has reduced volumes in key basal ganglia structures like the putamen and caudate, and undergoes a documented physical delay in how its cortical surface matures and prunes itself.
That delayed maturation is so critical.
From there, we watched the brain in action via fMRI blood flow tracking. We witnessed how the right inferior frontal cortex fails to command the necessary energy to apply behavioral brakes, resulting in impulsivity.
The failing brakes.
We saw how the left parietal and cerebellar regions struggle to keep the internal metronome ticking, resulting in profound time blindness and delay aversion. We moved out to the massive highway systems of the brain, discovering that internal distractibility is often caused by the default mode network, the daydreaming network, stubbornly refusing to switch off and constantly interrupting the cognitive executive task networks.
Or radio playing in the background.
Exactly. And finally, we looked at the absolute cutting edge of the field. We saw how the future is being shaped by artificial intelligence, where semi-supervised machine learning is mapping complex neurotransmitter densities directly onto brain structures to categorize precise, biologically unique subtypes of ADHD, paving the way for targeted, personalized medicine.
You summarized that perfectly.
When you lay all of that science out, from the 2009 Arnston paper to the 2025 Chen paper, you realize just how beautifully, intricately complex the ADHD brain truly is. It is not a broken neurotypical brain. It is a unique neurobiological ecosystem with its own specific rules, strengths, and vulnerabilities.
It truly is. The incredible depth of the neurobiological research available to us today paints a clear, undeniable picture of a brain that simply interacts with the world in a fundamentally different way, governed by distinct structural, functional, and chemical realities.
And that brings us to a final, lingering thought. I want to leave you with something to mull over on your own that builds directly on the source material we've unpacked today.
This is an important thought experiment.
We now know with absolute certainty from the extensive 2022 and 2024 review papers that the ADHD brain features a documented developmental delay in cortical maturation. The prefrontal cortex simply takes longer to build its infrastructure.
It's a biological fact.
We also know from Dr. Arnston's foundational 2009 work that this specific brain architecture results in weak, top-down executive control and a heavy, almost unavoidable reliance on bottom-up, stimulus-driven attention.
Right, reacting to the most salient thing in the room.
Now, look at the external environment of the world we live in today. Our modern digital world is almost entirely engineered by brilliant technologists to ruthlessly exploit bottom-up attention.
It's an attention economy.
Unpredictable smartphone notifications, the infinite scrolling architecture of social media feeds, rapid-fire short-form videos, the bright red badges, and the promise of instant digital rewards. These are all meticulously designed to bypass your top-down executive control and directly hijack your sensory cortices and reward centers.
They are engineered to be salient.
Given what we now understand about the neurobiology, how might this highly stimulating, incredibly fast-paced digital environment be interacting with or even fundamentally altering the neuroplasticity of the developing ADHD brain?
It's a massive question.
If a child's brain is biologically structurally delayed in its ability to build the infrastructure for top-down control, what happens to that development when the brain is submerged for 8 hours a day in a digital ecosystem that constantly rewards and demands bottom-up, reflexive reactions?
Are we making it worse?
Are we providing an environment that supports that delayed maturation, or are we providing an environment specifically engineered to overwhelm it? It is a profound, unresolved question about the intersection of human biology and modern technology, and it's something to deeply chew on the next time a notification buzzes in your pocket, overrides your top-down goals, and steals your focus.
Something to really think about.
Thank you for joining us on this deep dive into the neurobiology of ADHD. We hope you leave feeling a little more curious, deeply validated, and a lot more well-informed.